study other tests methods to check to prove whether the series is convergent or divergent. Before we do that, we have to understand the theorem, the following theorem. It says that this is a theorem. It says that if you're given a series, maybe the term is not necessarily positive, negative, okay? So given a series n start from n to capital N, okay? So we consider that series. So if that series absolute value, we put that absolute value, then become all the terms are non-negative. If this is a finite, then it is guaranteed this is a convergent. Okay. It is it is convergent. Okay. So intuitively, how do I understand this? This means the an, okay, absolute value n decays very fast in order to make this convergent. Okay. So then if we change signs, maybe n negative, maybe positive, then the change on the partial sum will be also small. So that's why eventually the original series is also convergent. Okay, but but conversely is not true. So let's look at the following example. Okay, a typical example is so this is an example, n starts 1 to from infinity. Okay, it's negative to the n minus 1 of n, right? So take a look at this series. All right, this series, this example shows you cannot the converse part is wrong. Okay, so this series is convergent. Okay, but this is a divergent. So absolute value of the term. Okay, it's divergent. Okay, so that means this example tells you those two convergences are not equivalent. Okay, but the other ones are stronger, right? Other ones are stronger. Okay, so we can say that anyways, n is convergent. Okay, so we give a definition. We say this is absolutely convergent. Definitely it's convergent. If this is a convergent. Okay, so we already know that it's because this origin series is convergent, so that's why we can say absolutely convergent. Okay, if it is, so that's called a. Now you also there's another definition called conditionally convergent. Conditionally convergent, then it's slightly different. So condition convergent means it is convergent, but it's not absolutely convergent. If this is convergent, but it's not strongly convergent, is divergent. Clear? Yeah, just a very weak convergence. All right, so according to the above definition, okay, we claim that this is conditionally convergent. No. Okay. Okay, this is condition convergent. Because why? Because if we remove that, but so very simple. If we remove the negative sign, it becomes divergent. Okay, but it's still, the series itself is still convergent. So condition convergent means still convergent, but it's not a strong convergent. Okay. Now, what is useful of that theorem, above theorem? What is useful above theorem? For example, if I ask, remember the problem we did, right? If I ask you to study this cosine n, right, of n squared, how to prove this convergent or divergent? Or you can, or beyond my ability to get any conclusion, right? So recall how many theorems we use, right? We nth term test for divergence. So we can use nth term to check whether it's divergent. Then I look at the nth term here. I think it's convergent to 0. So it's useless, that term. I cannot use that to prove its divergence. We cannot use, we cannot use the nth term for divergence, nth term test for divergence to prove it's divergent, because the nth term does not nth term approaches 0. Can I use the integral test? I have to prove this is decreasing, but it's hard to prove it's decreasing. Maybe, right? Integral test, but you have to evaluate the integral. Are you able to evaluate integral cosine x over x, right? So let's try them. This good example. So nth term test for divergence. Okay. First of all, let's look at the nth term. Yeah, suppose you don't have any experience, right? But you only learn, you are given a very toolbox here, lots of tools there. When you try one by one, right? And this is going to be 0, clear. Why it's 0? Because the numerator is bounded. The denominator is getting larger and larger. So that means this test does not work here. Okay? I cannot use that to prove its divergence, because this is a necessary condition. If it's convergent, then the limit is 0. It's 0, but 0 does not mean you can conclude it's convergent. Okay? And then let's try the integral test, all right? One by one. Integral test. Integral test, I have to look at this function. I want to make sure this is decreasing. Maybe we are lucky this time we can prove it's decreasing. Okay, we can. Let's try. But decreasing, but then we have to prove that this decreasing. Then you have to evaluate the integral. That's a challenge. That is a challenge. Okay, maybe we can. I don't know. So let's look at the derivative, right? If it's complicated function, you have to differentiate. This can be x to the 4th, and the cosine x is sine x times x squared minus 2x cosine x. Okay, I take x out, I get x cubed. So here's negative sine x times x minus 2 cosine x. I really don't know whether this is going to be negative or not. Okay, why? Yes, sine x times x, when sine x is away from 0, then it can be pretty large when for large x. But it's really, whether this is going to be negative, it's not clear. Yeah, this should be true for any larger number, right? For sufficient larger n, sine x may be very small. So that sine x times x still smaller than cosine x, 2 times cosine x. So stop here. Does not work. Okay, this idea does not work. All right. Can I use alternating series test? No. Alternating series test? No. Okay, it's not alternating series. Then what do you have? Comparison. Comparison tests? No. Why? No. The reason is the n term, cosine n might be negative. Right? If you want to use a comparison test, all the term must be positive. Remember, right? Then you can compare. Cosine could be negative. So they're all not working, right? Right. So then next step is to try our above theorem. Okay, I'm going to, maybe this is not only just convergent, strongly convergent, you know, I can, yes, it could be, you know, could be absolute convergent. So let's take a look at this. N squared cosine n. The reason is it's might be not be negative, so we have trouble. Now I put absolute value on that. If this is convergent, then I say it's absolute convergent. It's convergent guarantee. But then once you put the absolute value, then you have more theorem you can use. Look at, okay, it's not alternating series, but the integral test does not work, right? And the first one doesn't work, but the last one, comparison test maybe works. Okay, so this is the n, cosine n over n squared is less than or equal to 1 over n squared, right? Because cosine n, the absolute value is less than 1. Okay, so now this is our Bn. Okay, so this side is greater than 0. Yeah. So now we know that this square is going to be convergent. Okay, by the P-series test. Okay, then sigma. So then this one, not the origin series, you can say this is a cosine m, this is convergent by the comparison test. Okay, by the comparison test. Okay, got it. So then this implies the series is, now if you want to say absolutely, you can say that. If you just ask you whether it's convergent, then you just say it's convergent, okay? Because it's absolutely convergent. Okay, so I don't want to prove the theorem at the very beginning. If you're a math major student, you know, you can look at how this prove it, okay? So roughly speaking is, if it's absolute, you know, is a sigma of the absolute value for n's terms, it's convergent. That means the n's term really does not change too much each time when n increases. So when you change the sign, you can make less contributions because you subtract some things from the sum, okay, from the previous sum. So that means this is, yeah, you can show this is convergent, okay. Yeah. Otherwise, you see this sum, the partial sum, consists of positive part or negative part. Yeah, then maybe I should really explain to you. You have to understand this. Okay, look at the absolute value n, right? Absolute value n this n can be viewed as, right? This could be negative, could be positive, right? So if it's positive, then this is going to be n. If it's negative, it's going to be, yeah, let's write in this form, okay? All right. So that, what does that mean? That means sigma n k star from capital N a k, you can have a separate terms, okay? Those are the positive terms, positive n's, okay? All right? And then I separate them. This is going to be the negative. If it's negative, a case, you know, both positive term put together, negative term put together, you separate them. But each one, yeah, let's look at the positive terms. Positive terms, it's definitely the only, some terms is missing, right? So the positive terms is really, it's less than equal to absolute value of that, okay? So if this side has a finite number, when you take the limit, then it implies this is a finite, right? Because this is increasing, that's upper bound. So negative term, negative a case, if you take a negative sign out, right? Then you have, yeah, then you have only have a portion of that. So if you put a negative, if I put absolute value of this, okay, absolute value of this negative terms, then they're still less than equal to that. Okay, so that's why both, if you remove the negative sign, okay, so both, you see, this goes to, this is a finite, always a finite, okay? It's upper bound, that's a finite upper bound, okay? So that is the reason this one has a limit, and this also limit. Both are convergent. I just want to explain to you those two. This is going to be negative nk equals n. Okay, so those are the only considered negatives. So those are the convergent, and then of course this will be the both are convergent. This is where I want to show you. This is convergent. Yes, that's what I'm trying to explain to you, and both are convergent. Only, yeah, the positive terms, negative terms, this is convergent. And this is also convergent. To explain that, and explanation is here. If you look at, just to understand the positive terms, you collect the positive terms together, then this is going to be less than the sum of all the terms of absolute value. But all the terms of absolute value, it's bounded, okay, because it's convergent. So this one is always bounded by some large number. So it's increasing, then this convergent. Similar argument for the second one. Second one, all the terms negative, if there are any negative term there, and it's also convergent. Okay, so that's the reason absolute value. Yeah, this implies. So that means if this is a convergent, implies, okay, implies and this is a positive and convergent. Okay, it's going to be okay, and also implies if I put a negative here, I take a negative sign out, it's going to be, actually, if I use the notation, it actually is a, well, if I put a negative sign here, then all the terms becomes positive. So this is also equal to, okay. So both are convergent. Okay. So therefore, okay. Therefore, it is going to be positive ends plus the negative ends. Okay, so then it's convergent. Okay, I cannot say it's upper bound because it's when it has a bound. Otherwise, you know, this part is negative. This part is negative. The second term is negative. First term is positive. All right. So so it's very useful theorem, and yeah, sometimes when the numerator is very bad, okay, and then use that. Use this theorem is it's very useful. Okay. Now my next topic is this called the ratio test. Ratio test, if we consider n stuff from 3, yeah, okay, and then I cannot, yeah, n here is not necessary to be positive, okay, so I consider, yeah, consider this limit. I assume it's L, okay. It says that there are two cases, okay, assuming this exists, okay. If it's not exist, I cannot use that. Finite exists. Okay. It could be, yeah, just the two cases could be finite or positive infinite, okay? It's two cases. I assume that it's positive, okay? Then the first condition is if L is less than 1, then the absolute value of these terms is convergent. If this is convergent, of course, the original series is absolute convergent because you only consider absolute value, right? Second, if L is greater than 1, then what happens? The limit of the nth term does not equal to 0. It may be up or down, jump it. So that by the nth term test, okay? By the nth term test, this is divergent. Clear? I don't need to say that it's divergent because what is key point is this is going to be not going to be 0. Now, why this is true? Okay, why this is true? Okay, we do the following. Okay, here's the idea of the proof. Okay, we assume that L is less than 1, right? Okay, assume that L is 1. So absolute an plus 1 over an. Okay, because the limit is L, so I can make sure this is a between, this is a 1, this is L, here's 0, right? I can choose another L prime. This will be, so because there's L converging to L, so for sufficient larger M, this is going to be less than or equal to L prime, or R. I'm going to use R here because people prefer R. Okay, so this is R, right? For when? For N greater than or equal to a larger number, okay? Our series also is from capital N, so I'm going to use capital, yeah, okay? For some larger number, larger, sufficient large. Okay. So then you will get then you get something like a geometric series, because when I so this is true for any n larger than capital M. So how about for M? Right, begin with capital M, right? Then this is also M plus 1, A M plus 2, and so on, N plus 1, right? You multiply them out, okay? You multiply them out, each of them will be less than or equal to R. So it's R to the N minus capital M plus 1, okay? But all the terms here canceled out, okay? Those all canceled out. So what do we get here is right? In other words, it's less than N plus 1. I'm going to write it in the following form, okay? Cool. So I can call it another constant C. How about that? Doesn't really matter, okay? So it's going to be for N greater than or equal to N. So since I is smaller, right? Since I is smaller than 1, you are using the geometric series. So this one, okay, this R to the N plus 1, N starts from M infinity is finite by the geometric series. Test, okay? So that implies it's finite, okay? This is by the comparison test. We compare that, right? This two, we compare. Then that implies if N started from N, observer N is finite too, because really doesn't matter the first term. So I'm not going to keep giving you all the proofs. There's another called RootTest. I'm not going to prove, but I only give you this proof, okay? And just show you, you are compare the nth term, absolute of nth term was a geometric series, okay? If the limit is going to be L is then less than 1. If L is greater than 1, that means it's really very large. Actually, the numerator, the next term is larger than the previous term. When L is greater than 1, N plus 1 is larger than AN, the previous term. That's why it's never decays. So you cannot get 0. Okay, so that's all I needed to show to you. So now we look at the following example. Okay, so this is going to be a good example is right. Study this. Okay, A is non-tensor positive, could be negative. Okay, and the N can start from 0. Okay, doesn't matter. So 0 factor is 1. 1 factor is 1. 2 factor is 1 times 2 by definition. Okay, so 0 factor is always 1. Yeah, it's defined to be 1. Okay, not 0. Right, if we express it that form. So my N is this term. Okay, what is the best way to prove it's convergent? Can you use a comparison test? It's possible, but you don't know how large of A, right? So a little bit complicated, but it's still, you can do that for sufficient larger N, okay? So you definitely have to consider absolute value, because otherwise It's harder to compare. Whenever you want to use a comparison term, you have to look at absolute value of the terms. Okay? Then it's going to be here's A, 1, 2, n, right? And you see that when n is getting large and large, when n is getting large and large, as the numerator is somewhere stop here. The remaining part is really getting smaller and smaller, right? Yeah. Okay. So we don't know where we should start here. I think when n is greater than absolute value a. Okay. When n is greater than absolute value of a, for the simplicity, I assume that a is less than or equal to capital N. How about like that, right? Because a is not necessarily the integer. So I make it simpler. It's going to be capital N, blah, blah, blah. Then it's easy to understand that. Right? Okay? So this will be capital N, here's capital N, somewhere here, right? Can you find something which you can? I probably just need these two terms. It's enough. Okay, I need those two terms. Okay, this requires math. Yeah. So I need those two terms. I get n squared denominator. Capital N is fixed. Okay, the rest of them is just constant, but those parts will be less than 1, right? So put more details n, 1, 2, all the way to capital N. Then here's n plus, still n. Here's n plus 1, right? This is n minus 2, still n. Here's n minus 1, n, right? Then you will see that I can ignore those parts, no problem. I cannot get rid of the other one, okay? But that's constant. And you can also, yeah, so this is all collected, right? So this is going to be capital N, and this is n factorial. And then I have n squared, n minus 1 times n, right? Then as long as n minus 1 is greater than equal to 2, capital N. Because I want to make sure this is larger than that, right? Then some terms in the middle. So n is greater than equal to capital N plus 1. Okay. Yeah, or greater than equal to capital N plus 2 squared. Okay. So now you group them together, you will get n. Here's capital N plus 2. Okay, n factorial, this anyway is constant. And you have this. Okay, so you do have to get an estimate, and this is a convergent, right? So we know that sigma from n minus 1 over n is convergent. That is obvious because it's involved n squared. So therefore, you get a to the power n factorial is convergent. And you will see it's too complicated and it requires a very good math skill to get such kind of estimate, right? To get this kind of estimate. Yes. So what I'm going to do is I'm going to use a ratio test to prove that's a simple way to do, okay? So using the ratio test, my an is going to be a to the power n, right? All right. Right, so look at this. An plus 1 observer an, right? I'm going to find the limit. So simplifying this, all right. So after simplifying this is going to be, let's rewrite it. Okay, so now you simplify. Okay, so you get n plus 1. After simplifying, you only get these two terms. And clearly, it approaches 0 as n approaches infinity, right? All right, so that means the limit of this is actually going to be 0, which is much, much smaller than 1. Right, then by the ratio test, so you don't need to repeat the argument in the proof of ratio test. You can show that this is going to be a to the power n is convergent. So this convergent, of course, it's the origin series is convergent absolutely, right? So this implies all right. So this is the very useful series, useful test. Now we can also use the other method to prove this convergence. So our next method is called RootTest. Okay, it's a similar, and sometimes there's no difference. You can use one of them to give a nice argument. Okay, the RootTest. So you consider this series, okay, n start capital N to infinity. And not necessarily to be negative, okay, but we assume that the statement very similar. So assume that the limit exists or infinite, okay? N goes to infinity, the nth root, and this is supposed to be L, and it could be finite or positive infinity, okay, either way. Okay, so the case 1, if L is less than 1, then again, it's a similar statement. This is a convergent. Okay. The only difference here is just a limit type. Okay. Second, if L is greater than 1, could be infinity, right? Then the limit of n does not exist. Okay, it's not going to be 0. Anyway, it does not exist. It goes to infinity, grow up. Okay, so it's not going to just say it goes not. It's not going to be 0. That means could be does not exist. Okay. All right, so that implies y does not exist. Okay. Yeah, this of course then this implies the series divergent. So let me give you a brief idea. The idea of for the second part. Okay. I already did it for the first part for the first step. So here L is greater than 1. So that means you can take a number, okay, let R to be greater than 1, less than L. That's possible, right? Right? Then since the limit is L, So the nth root of n absolute is greater than equal to r for n greater than capital M, okay? For very large n. Because the limit is going to be L. Of course, it's getting close to L. It's greater than R. R is a fixed. Then from here, imagine this is greater than equal to R to the power N. Okay, so now it's much easier to see that. So clearly that's for N greater than equal to M. Now, if R is greater than 1, this implies right? Then this implies n is not going to be 0, right? Clear. That's it. All right, then by the nth term test, why the series is divergent. All right, so let's go back to some problems. You have here's the important fact. As the limit of n approaches infinity, square root n, this is going to be 1. How do you know that? We use this fact. Okay. We use this factor is we're going to e to the natural log of 1 of n is e to the 1 of n natural log n. So natural log of n over n approaches 0, right? Because natural log grows slower than any polynomial. So this clearly it's approach. You can use the L'Hopital's rule to prove that. So that's going to be 1. Got it? As n approaches infinity. Right, so this is a quick fact we're using. Right. So let's look at, I know let's look at n square and let's look at n square and 8. Let's see. I'm going to, yeah, so just look at n, okay? Check whether it's convergent or divergent. Okay, this is a good example. Can you use a ratio test? Yes. Can you use a, yeah, we can also use as a root test, okay, to look at. So let n to be the limit of n. So when I simplify, it's going to be numerated just absolute of a. The denominator is actually the nth root of n then square, okay? So it is going to be absolute of a, no problem. Okay, because nth root of n approaches what? So what is next step? Yeah, what is next step? Well, you have two cases. If absolute a is less than 1, right? Then this is absolute convergent. It's convergent. It is convergent, then you say this is absolute and not only just convergent, right? So this you can also directly can say that, and this is a convergent. It's absolutely convergent. Okay. Then absolute a is greater than 1. You can show that absolute of a in square, we already know that's going to be absolute, right? We already know that from above. So that implies the series is divergent. Why is divergent? The nth term, the limit is not going to be 0. So this is divergent by the test of a divergence, as the nth term test for divergence. Okay? Yeah, you should mention that too, by the nth term test for divergence. Okay. Yeah, this is a by the RootTest. Yeah, this is a by the, it's also by the RootTest, okay? But the RootTest argument is actually use a ratio, use an nth term test for divergence. Okay. How about absolute value a equals 1? Think about it. I'll give you a minute, okay? What happens when absolute a is going to be 1? Okay? So absolute a is greater than 1, a is going to be plus minus 1, okay? But it's okay. Absolute of a greater than 1 and absolute n is going to be absolute a to the n, right? N squared. So absolute of a is, you cannot use the ratio, you cannot use the RootTest, you cannot use the ratio. So actually it's going to be 1 over n squared. But this is a convergent. It's a still convergent. So we are done. But you have to use a different test. Okay. Now, there was a student, for some reason, always use a ratio test to try to figure out all the problems. But it doesn't work. If you use a ratio test, okay, to study this series, it's inconclusive. Okay, you cannot get any conclusion because the limit is always equal 1. Okay, the limit is always equal 1. Okay, so for example, yeah, if you just want to look at, yeah, like n, here's n cubed plus 1, such things like that. And they are, no matter which problem they use, they say, oh, this is good, I'm going to use a ratio test. The ratio test will not give any conclusion, okay? So n plus 1 over n, and what you get is very complicated, okay? And n over n squared, n cubed plus 1. But after you simplify, I promise you this is going to be, the limit is going to be approaches 1, okay? So if L is 1, and you look at the ratio test, you cannot say anything. Of course, you know, if you make mistakes, your limit is not going to be 1, then you get a conclusion. So if the function, if the nth term is a polynomial of another polynomial, you cannot use a ratio test, you cannot use a RootTest. Ratio test and RootTest only work for the exponential functions, okay, such things, okay. So if you take notes, you know, your own notes, you want to have a summary, then you should, yeah, record that, okay. So this only works for the, yeah, the only method works here is going to be what? Can you say this is a convergent over divergent? How do you prove that? How do you prove your claim? Right. So this the ratio test does not work here. Does not work for this series. Okay. So is it convergent or divergent? I think in order to see that, you just drop some important terms. only keep the leading term. So n over n cube actually can do that direct computation because it's n cube plus 1. So it's going to be 1 over n squared. The comparison test gives the answer. Okay? The comparison test gives the answer, and this is the stuff from n cube plus 1 is less than or equal to, and that is convergent. So you're done, right? Right. Another, what? Where's this from? Okay. Erase it. There's an addition software. Right. Okay. So here's my remark. We don't know how to handle this. Right? So we cannot use nth row test if you see n factorial in the nth term. Okay. Do not use the the root test for the convergence, okay, where n contains n factorial, okay, because you cannot figure out what is the nth root of n factorial, okay? So that means if you have a series like that, like a 2 to the power n, right? And okay, it looks like you should use nth term test, root test, right? Then the problem is, yes, the numerator looks fine, but the denominator, what is denominator, right? I think the nth root of n factorial is going to be infinity, but that's not given in the book. It's harder to prove it, right? It's harder to prove that. If you really have to prove this, okay? Because the ratio in the ratio test, the limit is going to be infinite, is going to be 0. So this, this question is 0. Why, right? So yeah, this should be 0, but it's harder to prove. Okay, in other words, the nth root of n factorial is going to be infinity. It's not, you can use a computer to check, a big computer, okay, doing very fast. If your n equals 1 million, do you really get a larger number, 1 trillion? Then you can, biologists always say jump to conclusion, yes, it's limited. And mathematicians say you have to prove it. Okay, it's not a, this experiment, only few experiments cannot jump to a conclusion. But in the top journal, Nature Science, okay, there are always some papers there and the people cannot repeat the same experiment. So maybe there's a cheating involved because they want to get a grant. That was a Japanese female scientist. She was laid off because of that, because nobody can repeat the same computation because the results are so important. So the people here in the United States that get $1 million taxpayer money, right, to reproduce the same result that fails, the West $1 million, very upset, right? And if it's successful, then can be used in medical, medical science. You can make new products, and that's why this is very serious business. Not the result. Yeah, you cannot make. So when you do the experiment, you take the biology courses. No matter what happens, don't modify, add something secret things in the result, or modify the data. That's not allowed. Okay, and eventually be discovered if it's good result. Yeah. All right. So I just want to tell you the difference. Even you test it, n equals 1, 2, 3, 4, 5, 100, 1,000. You find out the nth root of n factorial is getting larger. You still have to find a way to give a proof. And you can say, I can conjecture the limit is going to be infinity, the nth root of n factorial. But in mathematics, this is not the proof. Okay, other people cannot use the result in their argument. Okay. All right. So this for this one, the only method you can use is ratio test, because n factorial ratio test works very well, because n plus 1 factorial over n factorial is just n. Okay, this just equal to n. Yeah, it's n plus 1. So that can be easily simplified in the ratio test. So using the ratio test for the series containing n factorial. Okay, that's my yeah, that's my remark. Another remark. Use the ratio test for the series where n contains n factorial. Okay, if the ratio test does not work, you have to think about comparison test, direct comparison test. Okay, sometimes comparison test works. Okay. All right, so let's look at another example. Okay, no what? This was a problem, bonus problem on the previous one of the previous fun exams. Okay. So you see a power exponential function. So exponential function, you can use a ratio test, you can use a load test. That all works. Why? You see, the ratio test, why it works, like a to the n plus 1 over a to the n, right? It's going to be a. So ratio test sounds working. And then nth root of n is going to be a, right? So this is a, yeah, so ratio test might work, and the load test might work in both cases. But if you don't have a good math skills, you will not give me the proof. You probably, the argument is wrong. If the argument is wrong, even the conclusion is correct, you cannot get enough credits. Okay? You just by luck. You know, if you random pick up answer, is it convergent, divergent? 50% chance to get right. All right? So yeah, if the argument is wrong, then it's hard to give you credits. Okay? So we have to give you have to give a complete argument in order to get 4 credits. Okay? So 5 to the n, 3 to the n, 4 to the n. Can you tell this convergent divergent quickly? You cannot use a ratio test. You cannot use a root test here. Yeah, you cannot simplify. The key point is you cannot simplify easily. But everybody knows that this is true, right? Everybody knows that is true. Okay, so I think this is going to become divergent, and this is n. Divergent means I really needed to find a lower bound, push to infinity, right? The lower bound. I keep it 5 to the n. And I want to make the ratio smaller. I have to make the ratio denominator larger, right? Denominator larger, I have to replace 3n by 4n. How about like that? Got it? Okay. So that is going to be twice of 4 to the n, 5 to the n. And that is 1/2 5 over 4 to the n. 5 over 4 is greater than 1. So greater than equal to 1/2. You agree? Okay, so my n is never be smaller than 1/2. So that implies this never be 0. Just instant test. Works. And what I do is actually do the comparison here, right? Comparison test. So this sigma is n starts from 1 to infinity is divergent by the instant test. Because if it's convergent, then the nth term must approach 0. Okay? But I changed the problem a little bit. May I just turn upside down? Right. Yeah, I can say I start from 0, okay? Doesn't matter. Is it convergent? Anyone can give me an answer here?
The bigger your n, the closer you get to 0.
Ah.
But you have 1 at the time, there's an over 1, and everything else is under 1.
You have answer? What's the explanation? All right. If we just want to prove it's convergent, it's relatively easy. I already gave some ideas. 3n plus 4 to the n, right? And this is n. You just need to get the upper bound, right? And that's it's controlled by another bn. If bn is convergent, sigma bn, then it's convergent. So 3 to the n is less than or equal to 4 to the n, right? Right? And that's going to be twice, right? 4 to the n over 5 to the n. Okay? So now it's 2 times 4 over 5 to the power n. So that is my bn. All right? Bn is convergent. N starts from 0 to infinity. It is going to be 2 times 5 over 4, 4 over 5. It's geometric series. Okay, so not only that, you will get, take a 2 out. This is I is smaller, I is going to be 4 over 5. It's smaller than 1. So it's 1 over 1 minus 4 over 5. And that is going to be 2 over 1 over 5, so which is 10. So not only find it, I even can get the answer. Okay, 10. Okay, so it's convergent. So that implies sigma n start from 0. It is convergent. Okay. Now actually you can get as a sum of this two, because yeah. So you have to you can choose, this is actually sum of two series. Okay? The sum of the two series, and each series is going to geometric series. So you can separate. It's just like an integral. 3 over 5 to the power n plus, and you can evaluate. Okay? If the starting term is n equals 0, then this is going to be 1 over 1 minus 3 over 5 plus 1 over 1 minus 4 over 5. And you simplify it, you will get 5 over 2. Okay? And you also get, here is 1 5 is 5 over 1. Okay? It's going to be 2 2 15. Okay, 15 over 2. Okay, it's not only fine, it's convergent, you also get a limit. Get the final sum. Yeah, here's the question. Last one, maybe. Is it convergent? Maybe I put factorial here. Okay, now compare these two. The only difference here is n factorial 2 to the n square, okay? Which one, you can, yeah, sometimes write in this or this. Okay? Is it convergent? Yes, yes. Let's look at the first one first, okay? Yeah, we can maybe do the next. N factorial of 2 to the n square. Okay, I cannot use a comparison test, integral test to forget it, right? I cannot see whether the limit is going to be 0 or not, right? The nth term. If it's obvious to me the limit is going to be not 0, then it's divergent. Maybe it's convergent because 2 to the n squared is slightly, grew slightly faster than exponential function 2 to the n. So I'm going to try two different methods. Is n plus 1 over n, okay? I see the limit. It's a little bit complicated, but don't give up. Right? Yeah, you have to write down clearly. Then here's n plus 1 factorial over n factorial, no problem. This is 2n plus 1 squared, that's 2n squared. So that requires your algebraic simple algebra skills. How do you simplify it? Okay, so this side is going to be n plus 1, no problem. And here, to simplify it, I need a 2 to the n square plus 2n plus 1. So I just separate 2n plus 1. So this will be canceled out. So my result will be this. This clearly approaches 0. Should I say more about that? This definitely approaches 0 as n approaches infinity. Okay? Why? Because the denominator numerator exponential function numerator is just polynomial. 0, 0, right? Approaches. You know, you can use the RootTest rule to check. Okay? It's obvious. So this is 0. That means the limit of n plus 1, because they're all positive, don't worry about the this means 0 is less than 1. So that implies convergent, right? Is convergent. Okay, done. But let's try to use a ratio test. You know, some problem you can use both. Okay? Some problem you can use both. So let's recall the n. N is n factorial. No, it's not working because n factorial there. I said n factorial cannot use ratio test. A RootTest test, n's RootTest test. The RootTest they have a problem. So the n is going to be square root of n factorial. 2 to the n. Right? But this converting to what? We don't know. Right? We cannot use a RootTest. Yeah, we cannot use a RootTest. We cannot use the RootTest here. Okay,